everyone. Welcome to the second part of the 26th lecture in the series Mathematical Methods for Economics. In the first part, we were talking about implicit differentiation. We introduced the method of implicit differentiation, and we also talked about what we mean by functions that are explicitly defined and functions that are implicitly defined. And we said that when we have an equation, when we have to differentiate functions that are represented by equations, then we don't need to worry about expressing the function in explicit form. We can straight away go ahead and differentiate both sides of the equation to find the derivative, or dy by dx. We will now continue with our examples and see how the method of implicit differentiation works in all its flavors. So, the example here that we have is one where this equation x times root y equal to 2 defines y implicitly as a differentiable function of x. Now, if you notice, the question still is that we have to find dy by dx by implicit differentiation, but the structure of this equation requires some more detail, because first of all, y, the variable y, since it is under the square root sign, we have to restrict it to being positive. And let's back up. Actually, neither, if you notice, neither one of the variables x or y can be 0, because if either x or y is 0 on the left hand side, then we'll have a 0, but that can't be equal to 2 we have 2 on the right hand side. So the first observation here is that neither x nor y can be 0. The second observation is that because the variable y is under the square root sign, we can only take the square root of a positive number here. So, y has to be positive, y is restricted to being strictly greater than 0. And because we are taking the positive square root here, which is here square root of y, that then has to be multiplied by a positive number in order to get something positive on the right hand side. So, x is also restricted to being something positive. Okay, so that is why we have both x and y being positive, which is to say that this the graph of this equation will lie in the first quadrant. Now, in order to be able to find dy by dx, we can differentiate both sides of this equation, x times root y equal to 2 with respect to x, and here we will get x times, now the derivative of square root of y with respect to x would be half times y to the power minus half times dy by dx, plus the second term, which is square root of y, we are using the product rule here. So, square root of y times the derivative of x, which is 1. So, that is our second term in this equation, that is then equal to 0. So, here we can take square root of y to the right hand side and then solve this equation for dy by dx, and that will then give us dy by dx equal to minus 2, because we can cross multiply here. So, this 2 comes here to the right in the numerator. So, minus 2 times y, which because square root of y into square root of y, once you cross multiply, will give you a y, and that will be then divided by x. So, dy by dx is then equal to minus 2 times y by x. Another way in which we can find dy by dx here is that we can actually square each side of the equation. This is an alternative method that we can follow, and we can write y here because x squared times y is equal to 4 after squaring both sides of this equation. So, this implies that y is equal to 4 divided by x squared, or 4 times x to the power minus 2. So, that when you differentiate y with respect to x, dy by dx is then equal to minus 8 times x to the power minus 3, or minus 8 divided by x cubed. So, this is where you are saying that you are writing y explicitly as a function of x, and let us see if our answers match, because earlier if you go back to the previous slide, we got dy by dx equal to minus 2 times y by x, right. Now, because y here is equal to 4 by x squared, then we are going to get minus 2 times 4 by x squared. So, that is nothing but x to the power minus 2, and that is then divided by x. So, that is nothing but minus 8 by x cubed. So that indeed is the same answer that you get. But some of you might be thinking here, and that might be that's a good way if you're thinking through things in this fashion, that our equation originally, because this equation was defining y as a differentiable function of x, and this equation was such that both x and y were positive, so that clearly the graph would have been restricted to the first quadrant. Whereas if you solve for y, you're getting 4 by x squared, and this is a graph we've already discussed, though we can't get into too much detail because we haven't done all the calculus so far for drawing the graph of such functions, but let me show you the visuals. So x times root y equal to 2 basically looks like this. As I said, it lies in the first quadrant, and if you look at the graph of x squared y equal to 4, which is what you get when you square both sides of x root y equal to 2, that is a graph which looks like what you have in the picture here, where the graph what you had for x times root y equal to 2 is now also getting mirrored on the other side of the y-axis. So you have these two parts to the graph. Now, many of you might ask this question that we have squared this equation, and the function, the information that was embedded in the equation x times root y equal to 2 has now changed, because earlier our function was just, this is the actual function which is represented by this equation, and now it's changed to these two curves in the two quadrants. So, is this a right approach to follow? Can we is it okay to square both sides of the equation and square it to get your dy by dx? The answer here is yes, you can do that straight, you can do that with no problem at all, because remember, the objective here is, our focus here is not on the graph as such. Our focus here is to be able to find the derivative at a particular point on the graph. Now, our graph, the original graph still remains here in the first quadrant. So, if I specify a point, let's say x equal to 2, because x has to be positive. So, let's say x is equal to 2, then in that case y is equal to 1. So, our graph is, if we want to take the derivative, there is no problem in taking the derivative, because we would be restricting ourselves to the points only in the first quadrant, right? So, in that sense, what you have in the second quadrant will not matter. The graph has changed, but still you can find the derivative. You can still find the slope of the tangent to your graph, which is represented by x times root y equal to 2 in the first quadrant. I hope that message is clear. Okay. So, that was as far as x times root y equal to 2 equation was concerned. Now, here I have taken this example from the Sitzeder and Hammond textbook. There is one which is the core textbook for the mathematical methods course, but there is also a book which is titled Essential Mathematics for Economic Analysis. And the question here is, suppose y is defined implicitly as a function of x by the following equation, where g is a given differentiable function of one variable. So, our equation is x times y plus 1 the whole squared is equal to g of x squared y. G is a function, and because y itself is a function of x, it is defined implicitly as a function of x. So, the g function will eventually become a function of x only. So, again the question is, find an expression for y prime or dy by dx. So, when we differentiate both sides of this equation with respect to x, we get 2 times xy plus 1 times the derivative of this expression in brackets. So, x times dy by dx plus y times the derivative of x, which is 1. So, that is what you have on the left hand side. And on the right hand side, when I differentiate g of x squared y, I get g prime of x squared y, and then that is multiplied by the derivative of this expression x squared y in brackets, again the chain rule at work. So, here we get x squared times dy by dx plus the second term y times the derivative of x squared, which is 2x. So let's just simplify this a little bit. Let's just get the algebra in place. So I can take 2 common here and open up the brackets on the left hand side. So I have x squared times y prime plus xy prime, right, plus xy squared plus y when I open up the brackets on the left hand side with the 2 outside. And on the right hand side I have g prime x squared y times x squared y prime plus 2 times xy, the same thing as what you have in the previous step. Now you can collect the y prime terms. So that will then give you 2 times x squared y plus 2x from the left hand side. And from the right hand side you have minus x squared g prime of x squared y. So all these are the terms which are containing y prime, and then on the right you will collect the rest of the terms, which would be 2xy times g prime of x squared y minus 2 times xy squared minus 2 times y, and then you can always solve this. So we then get y prime equal to 2 times y. I can take y common on the right hand side and the 2 as well. So 2 times y times x times g prime minus xy minus 1, and the whole thing is divided by, I can take x common for all these terms in front of y prime. I can take x common, I get 2xy plus 2 minus x times g prime, and that's your expression for dy by dx. Okay. This is another example that I have from the textbook, and this example is interesting because it kind of shows you how to leverage the method of implicit differentiation to be able to do something something different as well. So here we have the power rule basically, and if you remember, we in the earlier lectures, if we have, let's say, y equal to x to the power a, y is a function of x and a is, let's say, any arbitrary real number, then dy by dx is equal to a times x to the power a minus 1. In fact, in the earlier lectures we had proven this power rule only for positive integers or for negative integers. And now let's just take things a step further. So it's like if y is equal to x to the power m by n, where m and n are integers, and we'll restrict here that n is the second one is not equal to 0, then the power rule gives us that dy by dx is equal to m by n times x to the power m by n minus 1. So let's verify this result by differentiating the equation, assuming that y is differentiable. You have to differentiate the equation y to the power n is equal to x to the power m. Differentiate this implicitly with respect to x. Now, once you differentiate this implicitly with respect to x, on the left hand side you are going to get n times y to the power n minus 1 times dy by dx, right? And that is then going to be equal to m times x to the power m minus 1. Now, because m and n are integers, we can always use the power rule for integers. We have already proven that. Okay, so let's now just simplify things a little bit, because we know that y is equal to x to the power m by n. I can therefore on the left hand side write n times x to the power m by n, right, the whole thing multiplied by n minus 1 times dy by dx is equal to m times x to the power m minus 1. And once I simplify this, because you can see here the n here in the m by n will cancel out the n in the first term in n minus 1. So I'll get n times x to the power m minus m by n times y prime is equal to m times x to the power m minus 1. This then I can solve for y prime as m by n. I can take n to the right hand side. So m by n times x to the power m minus 1 divided by x to the power m minus m by n, and then you can just simplify this further. You take m minus m by n to the numerator. You can see that the m's will get cancelled, and you're going to get exactly the result that you want, which is that dy by dx is equal to m by n times x to the power m by n minus 1, and that is your power rule for rational numbers, where the power is a rational number. So, till now we have talked about taking the first order derivative for functions defined implicitly. Let us move a step further and also talk about the second derivative of functions which are defined implicitly by an equation. And here we will go back to our earlier examples. So, for example, if you take the case where the equation was given by x times root y equal to 2. So, let us calculate y double prime for the equation here, for the function that is implicit in this equation here. Now, the answer that we had got earlier, the result that we got was y prime equal minus 2y divided by x. So, here we can use the quotient rule for differentiation to differentiate the equation y prime equal to minus 2 times y by x implicitly with respect to x. And while taking into account that y is a function of x, I can now differentiate y prime equal to minus 2y by x. So, that is going to give me on the left hand side y double prime, which is d2y by dx squared equal to, we will keep the minus 2 separate because that is just a constant. So, that will then give me the denominator when I use a quotient rule, denominator x times the derivative of the numerator with respect to x, which is y prime, minus the numerator, which is y, times the derivative of x, which is 1, the whole thing divided by x squared. Okay? And this then is equal to minus 2 by x squared. I can take these out, and then in the parenthesis I have x times dy by dx, because dy by dx was minus 2y by x. I will substitute for dy by dx, minus 2y by x, and as you can see here, the x terms will get cancelled. Then I have a minus y in the numerator, so that is something I have put here again. And once you solve for that, because after the x's get cancelled, in the parenthesis I simply have minus 2y minus y, which is minus 3y, and that multiplied by minus 2 is 6y. So, the result that I get here is 6 times y divided by x squared, right? And again, if you want, you can always express this in terms of in terms of just x, because y is equal to 4 by x squared and y prime is equal to minus 8 by x cubed. We can substitute for y here. So, y is in this case, actually if we do it by the implicit, by the explicit form, minus 8, because y prime is minus 8 times x to the power minus 3, then dy by dx, d2y by dx squared would be 24 divided by x to the power 4. And you can see here that once I substitute for y, which is 4 by x squared, that also gives us 24 by x to the power 4. We get the same result whichever way you want to do the differentiation. So, this is how we can calculate the second order derivative. Let us take up another example. So, here we have the equation x minus y plus 3 times xy is equal to 2. So, the question is asking you to find y prime and y double prime by implicit differentiation when x minus y plus 3 times xy is equal to 2. So, again differentiating both sides with respect to x, we have 1 minus y prime plus 3 times x times y prime plus 3y. Here you can use a product rule. So, 3x times the derivative of y with respect to x, which is y prime, plus y times the derivative of 3x, which is 3. So, that is then equal to 0. When you solve for y prime, you are going to get 1 plus 3y divided by, if I take y prime to the right, I am going to get 1 minus 3x in the denominator here down below. And this equation then I can use to calculate y double prime. So, here again I will be using the quotient rule. In the denominator I will have 1 minus 3x whole squared, and in the numerator I will have the denominator 1 minus 3x times the derivative of the numerator, which is 3 times y prime with respect to x, minus the numerator 1 plus 3y times the derivative of the denominator with respect to x, which is nothing but minus 3. And here when I just simplify, I can simplify the numerator. Let me just, so what I have done here is I have brought this 1 upon 1 minus 3x whole squared out just to free up the space. So, yes, y double prime is this expression here if you look at this particular equation. And this then, if I just open up, if I open up the brackets and substitute for y prime, so y prime is 1 plus 3y divided by 1 minus 3x. That will cancel out the 1 minus 3x in the numerator. And then I have minus 1 plus 3y times minus 3. Okay. So that actually boils down to something quite simple, because I have a 3 times 1 plus 3y, and again another, because the minus and minus will become plus. So another 3 times 1 plus 3y, that's nothing but 6 times 1 plus 3y, the whole thing divided by 1 minus 3x the whole squared. Those are our results for the equation x minus y plus 3 times xy equal to 2. Y prime is equal to 1 plus 3y divided by 1 minus 3x, and y double prime is 6 times 1 plus 3y divided by 1 minus 3x the whole square. Again, if you want, you can always express these y prime and y double prime only in terms of x. So for example, I've done this for y double prime, you can do it for y prime on your own. So y double prime, if I were to just express everything in terms of x, I just have to substitute for y here, because here I can explicitly solve for y. If you notice here, y is nothing but 2 minus x divided by or x minus 2 divided by 1 minus 3x. So if I substitute for y, I have in parentheses in the numerator 6 plus 18 times, so that will be, because that's 6 times 3, 18 times x minus 2 divided by 1 minus 3x. I've just substituted for y, and that then gives me 1 minus 3x the whole cubed in the denominator, and when I cross multiply with 6, I get 6 minus 18x plus 18x, the 18x terms will get cancelled, minus 36, so that's minus 30 in the numerator. Our answer here is then y double prime equal to minus 30 divided by 1 minus 3x the whole cubed. Okay. So this is how we go about using the method of implicit differentiation to calculate either dy by dx or d2y by dx squared. And the idea here is that you don't have to worry about whether the function can be expressed in explicit form. It may well be that here you may have a function which is defined implicitly as a function of x by a particular equation, but you always have the method of implicit differentiation to be able to solve for the derivative. Okay, so we will end this talk in this video by one more example, which is slightly different from the ones that I've done earlier. Here you have y, which is expressed as an infinite series, and we have y equal to x plus 1 by 1 by x plus then again the denominator here 1 by x, and it just goes on. So because one way to, so the way to approach this kind of an equation is that because we have an infinitely large number of terms, we could always ignore one, let's say one of these terms, let's say x. So we could write y as x plus 1 by y. So this whole thing in the denominator, this can represent our y, because in any case we have an infinitely large number of terms. So ignoring one term x will not make a difference, and here we can get something which is more tractable in order to find our dy by dx. And actually that makes things very simple, because once you write y as x plus 1 by y, you can take the LCM, and now you have the equation being stated as y squared equal to x times y plus 1. This, when you differentiate both sides with respect to x, you're going to get 2 times y times dy by dx on the left hand side, and on the right you'll have x times dy by dx plus y by the product rule. And then collecting the terms containing dy by dx, we're going to get dy by dx equal to y divided by 2 times y minus x. So this is an interesting problem. It gives a slightly different flavor to things as against what we've done in the other examples. And I'm afraid we'll have to conclude here, because I'll need some more time to talk about total differentials. So we will talk about that in the next video, and in the next video I will also take up some economic applications of implicit differentiation. So I conclude the second part of our discussion on implicit differentiation here. Thank you very much.